Hi, I'm Randall Hayman, a university mathematics academic, and you're on one of my Corona Help playlists where I make quick turnaround videos for educators and students. If you'd like me to make you a video, then just comment below any of my videos or drop me an email, and if I think I can help you, I will. So we've been clocking through quite a few things in analysis, and I wanted to mention completeness and Cauchy sequences, which I think rounds off what we've been talking about, and after that I'll do one more on topological spaces, and then that's probably sufficient for the people who have asked me for videos in this area. But obviously if people want more, I'm happy to do more. Just ask. Okay, so what have we got here? Well, let's talk about convergence, which we've mentioned before a few times, I think, convergence. So you'll see this sort of thing, a sequence, AN. So here we're thinking AN equals, I don't know, 1 on N or something like that. So it goes 1, a half, a quarter, but whatever. In a metric space, and I'll write it X with rho. Rho's that metric that we use, that distance measure that we use. And we say it converges to a limit L if for every epsilon greater than 0 there is an N such that the distance from the AN to the limit is less than this tolerance, this epsilon tolerance, whenever little n is greater than big N. Okay, so what's the picture that you want to have in your mind here? Just draw a nice little diagram, and that might help. Okay, so let's put there, and let's put an axis here, and also I think I want something in blue here, so let's go about there. That'll work well. So let's draw a little line here. Whoops. Okay, so this is X and this is Y up here, and this is L, the limit. And so what we've got here is these ANs which are getting closer and closer to L. And this is saying that if you give me an error term, any error term, so this here is now, this distance is epsilon, the error or the tolerance, well then I can give you a big N, say here, and whenever N is greater than N, which is here, sure enough, the ANs are all less than epsilon distance or metric from L. So that's the idea. Now, there's a couple of problems with this. One is, well, there's more than a couple, but there's two things I want to highlight. One is, let's talk about this L. You can see if we want to prove that something that it converges, we have to know what it converges to. So you have to know the limit, what it converges to actually show that it converges. The second problem that you could have is that this L might not actually be an element of X, this space. So that's another problem. So people came up with another concept called Cauchy sequence, Cauchy named after the mathematician. Cauchy sequence. So a sequence is Cauchy, or you could say it's a Cauchy sequence if you want, if in a metric space X row, if given an epsilon greater than 0, there is some n, so it seems pretty similar so far, some n such that that distance on the metric from am, say, to an is less than epsilon whenever m and n, little n, are greater than n. So this is an interesting idea because this is giving a definition of a Cauchy sequence. It's not saying it's convergent, but it's saying it's a Cauchy sequence, similar sort of idea, but we're just looking at the sequence itself. It's an intrinsic sort of idea of convergence because it just relies on the sequence itself. There's no need actually here to work out what it converges to. We're just looking here. If you look here, we're just looking at elements in the sequence. Okay, so interesting fact, every convergent sequence is Cauchy, but it unfortunately doesn't work around the other way. And the key aspect is completeness. So a metric space is complete if every Cauchy sequence converges to a point in X row. So a metric space, I suppose I should put up here, X row, is complete if every Cauchy sequence converges to a point in the metric space. So that's completeness. Now there's some nice examples from everyday life, or everyday mathematical life. The Q with the normal, let's talk about the metric space Q with the normal distance measure. So distance between A and B is just the absolute value of A minus B. So that's just the normal concept of length in the real world. Now Q, this is not complete. Why? Well, I can show you an example. Let A n equal pi to n decimal places. So A1 is equal to 3.1, A2 equals 3.14, etc. Well, it's easy to see this is a Cauchy sequence. Why do I say that? I'm not going to prove it. Good exercise to actually write it out, but I mean, you can see once we get to, say, this 2, A2, anything after this is well, they've all got 3.14 to start with. So the distance between the distance here between the any AN and AM is certainly less than 0.01. And you can fashion it in that way to wherever you want. You give me any error or epsilon, I can easily work out how many, what big N I need to make that all work. But this is a Cauchy sequence, but the limit, well, let's put it this way, better still. AN approaches pi, which is not an element of the rationals or the fractions. So this is an example where Q is not complete. On the other hand, of course, R is complete. So I think that's all I wanted to say about Cauchy sequences and completeness. And if you've got any questions on that, please let me know, and I'm happy to do more on it. It's quite an interesting area. I'm happy to do more if people have got an interest in that or something that they need to get done for an assignment. So let me know. And more generally with anything in mathematics, just drop me an email or comment me below any of my videos. Thanks very much.